Okay, so we are still trying to find the properties of pure substance. That's what we are trying to find. And we have been discussing about property table and how we can find the properties using the property table. We'll do one numerical problem. We'll continue on what we have been doing, and other is we'll describe about ideal gas equation. So those are the two things which we will try to do in this lecture. So I think this question we started from last time, and we are done with A and B part. We will continue on CDE. So we would like to fill in the blanks. So when you submit your class participation work, it is important to show the detailed work. It's not just filling out here. You need to show the detailed work when you solve this problem. Okay. So we are done with part A, B in the last class. So this is part B, and now we are moving on to part C. Okay, so this is part C. So what we have here is part C. This is part C. That's what we are focusing on right now. Now we need to see what is given here. So in this case, this is a pressure which is 1000 kilopascal, and a specific internal energy in kilojoule per kg is given as 2950. So this is what it is given. So that means you are given pressure and one property U is given. So you need to figure out in which case does it fall on. So this is a case in which either pressure or temperature is given and then property is given. So this is a case 2. So in this type of uh, problem, we need to compare the property. We need to compare the property with the saturated liquid and saturated vapor, which does mean that we are comparing the value of specific energy with the saturated liquid and saturated vapor. Okay. So we need to figure out where it lies, right? So again, for that, at this pressure and a specific volume, something is going wrong here. Let me check. Okay. So if you look at the table for the pressure table, if you look at the table for pressure, um, and find the value of subscript F and G, and compare with whatever the value you have, and figure out where it lies. So for that, the starting point would be A5, which is a pressure based table for water SI unit, and then once you know where it lies, then you can use either A6 or A7, or it could be A5 as well. So let's try to see from the table where it lies. So at this is A5, which is a pressure based table, and at 1000 kilopascal, this is internal energy. The values are given here. Now you need to compare this with the U value. So UF is this one, UG is this one, UF is this value, and you could see here the value of U is greater than UZ. So in the TB diagram, if you see here, so this is Z here at this, um, so U, this is UZ, so it's greater than U. U is greater than UZ, which means it is a superheated region. Now our goal is to find the pressure is given. Now we know it is a superheated region. Now next goal is to find the temperature for this value of U. So that is the next goal. So we know it is in the superheated region, so we need to look at table A6. So that's the next step. Now we know the pressure is 1000 kilopascal, and the pressure table in superheated region are in megapascal, and 1000 kilopascal is 1 megapascal. 1000 kilopascal is 1 megapascal, because 1000 and then multiplied by kilo is 10 to the power 3, which is pascal, so it becomes 1 into 10 to the power 6, and 10 to the power 6 is mega. megapascal. So you need to look at 1 megapascal. And what is the value given? This is the U value given here. Now we need to find the temperature corresponding to this U. So that's the goal. So 2950, where it lies? So you see here it lies between this 2875 and 2957. Okay, so it lies in between this 350 and 400 degree temperature. So it's not given exact. So this is where the interpolation comes into picture. So we need to do the interpolation to find the unknown value of temperature. Okay, we need to, so U lies between 350 and 400 degrees centigrade, and these are the value. So at this value, T1 is 350, U1 is given, T2 is 400, and U2, and you need to find the T when U is this is what it is given here. So you carry out the interpolation like we discussed before, and the only unknown is temperature. If you substitute the value, so the unknown temperature is 395.2 degrees centigrade. Since it is in the superheated region, we don't have to worry about quality. You don't have to worry because you don't have quality. You don't have to calculate quality in superheated region. So we calculated the temperature, the pressure, and property value is given, and it is a superheated region. In superheated region, we don't have to worry about the quality. Okay, this is part C. Now we will move on to part D. So this is part D now. This is part D. So here again, you need to see what is given. So here pressure is given, and temperature is given. Pressure and temperature are given. So if pressure and, this is a keyword, not R, it is and. So if pressure and temperature are given, then you should always compare this with P saturation and T saturation. That's what you need to do. For P saturation, you need to look at the temperature base table. For T saturation, you need to look at pressure base table and compare with the value whatever is given here. And again, from exam point of view or the homework point of view, you don't have to look at all the table. If you just find in one, it's all good for calculation. So you don't have to look A4 or A5. If you just look at A4 and then compare the pressure value, that's also fine. So the key is, in this case 1 is what we are doing. If pressure and temperature given, you need to compare with the saturation pressure or the saturation temperature. Okay, so given 500 kilopascal, and so this is if you want to look at the pressure base table, or you can look at temperature base table. So at T equals to 75 degrees centigrade, which is A4 table, you find that, so this is A4 at 70 degrees centigrade. So this is, what is the temperature? At 75, so this is the temperature you have. So this is the temperature which, so temperature, this is the pressure which you have. So this is the pressure you have, saturation pressure. And if you look at A5, at this pressure, this is the saturation temperature. So what conclusion can you make from here? So at 75 degrees centigrade, our pressure is 500, and here the pressure is 38.597, and then at 500 kilopascal, saturation is 151.83, which is less than this. So here T is less than T saturation in this case, and then P is greater than P saturation. So it is a case of subcooled region or compressed region. And in subcooled region, in order to find the property, so we are interested in finding U. We don't have to worry about X because it is only in the saturated mixture region we are interested in. Phase description is subcooled or compressed liquid, so we are interested in finding U. And in the subcooled region, the easiest way to find the property is U is equals to UF at that particular temperature. So in the subcooled region, the properties are function of temperature, and this is how you can find the temperature. Okay, so you can look at this temperature. So you can look at the temperature table, and you see that at 75 degrees centigrade, U is 313.99 kilojoule per kg. Okay, so this value at 75, and then internal energy, uh, you have here UF value, so that's what it is. So this is how you can find the property value. So again, you don't have to worry about the quality, because in compressed region we don't talk about quality. It is only in the saturated region we are interested in finding the value of quality. So you can say kind of not available. Again, remember, when you submit your class participation work, you need to show this detailed work, not just the fill in the blanks. Okay, now let's move on to the E part. So in E part, what is given here? Pressure is given, and then quality is given. Okay, so whenever the quality is given, it is a case 3. Okay, so x equals to 0, that quality, what does that mean? So here, this is saturated liquid, so this is x equals to 0. This is saturated liquid, so you need to find the property at this pressure, which means this is subscript F. So 850 kilopascals, which is pressure based table A5. So 850 is here, and then it is a saturated liquid, and then you want to find the value of internal energy, right? So which is U equals to UF, and so this is internal energy, and then this is what it is. So this is UF, which is a saturated liquid, so the value is given here. So this is how you can find the property. So I think we know everything. Oh, okay, we still have to know what is the what else do you need? Oh, the pressure is given. Pressure is given. Pressure is given, and so this is UF, and the temperature relates to, when here we are assuming it to be here is a saturated liquid, so corresponding to this pressure 850, you need to find out how much T is the T saturation. Okay, so this value is given here, so it is in the saturated region, so 172.94, which is a saturation temperature corresponding to 850 kilopascal. So this is the temperature, so we kind of fill in the blanks everything. Again, you need to show this detailed work, not just the fill in the blanks. So that's about this combined complex type of problem. I hope you understood how to solve the problem using the property table. Next is there are other ways by which we can find the property for superheated vapor or other gases. So other gases could be like nitrogen, it could be oxygen, it could be carbon dioxide. And we know what superheated vapor is. So you know, if you have a vapor something like this, so in this region, so this is the superheated region that we are concentrated on. Okay, if it is a superheated region, we already know how to calculate the the property using property table, but it's most accurate, but it's so much of data, bulky, so that's kind of drawback. The easy way, you might have already done in chemistry, how to find the property using ideal gas. So this is the very common way to find the property, but it is the most is the least accurate. Okay, and the easiest way. And there is also another way, which is called compressibility factor, and in that case we use the chart and formula, and the accuracy is kind of in between ideal gas equation and property table. Very important thing, whenever you are using ideal gas equation and compressibility factor, you should never, this is important, never use for solid or liquid vapor mixture. These two equation can only be used, so ideal gas equation and compressibility factor can only be used for gases and gases. Okay, you never use for the liquid. I have seen in the exam, you're said like this is a liquid or solid, and you tend to use ideal gas equation. That is absolutely wrong. Okay, you cannot make use of ideal gas equation when it is a liquid. By the name itself, it suggests gas. Okay, so it has to be either superheated vapor, or it could be gas like nitrogen, oxygen, carbon dioxide. Only in those cases, when it is a gas, only then you can use the ideal gas equation. So if it says liquid water, never use the ideal gas equation, never use the compressibility factor equation. Okay, of course we know we can use the property table, but ideal gas equation and compressible factor chart must be used only for gases and superheated vapor. And we'll talk about, under which condition this superheated vapor can be used, um, using the ideal gas equation. We'll talk about that later on. Okay, but never use ideal gas equation for liquid and solid, or mixture of, even you should not use for the saturated, uh, mixture of saturated liquid and saturated vapor as well. Never use that. So this is a very important consideration, because that's where I see, you tend to make mistake. Okay, so please remember that. So if you see here, finding the property for superheated, one way is to use the property table. For water is A6. The other way by which you can is ideal gas equation, which relates pressure, specific volume, and temperature. And then third way is ideal gas equation with the compressibility. Um, so this is what we will be discussing next. So I think for today I'll discuss the ideal gas equation, and maybe on Monday we'll discuss about compressibility chart. So this is the equation for ideal gas equation. Equation is PV RT. We should understand what each term means, and the difference is you have this Z in the compressibility chart Z. Okay, we'll talk about that's the difference between these two. So this is additional term in compressibility chart. Okay, now since we are trying to discuss about ideal gas equation, okay, so we first describe what equation of state is. So the equation of state relates pressure, temperature, and specific volume. And the simplest uh, uh, equation that relate pressure, temperature, and volume for gas phase is called ideal gas equation. And the equation is P V equals to RT. Okay, it's important to understand what each term means. And in this type of, whenever you do the numerical problem, the units, that's the most important thing. You tend to get mistake in units when you do the calculation, so you should know exactly what each variable mean, and what is the unit of each one of these variable. Like pressure is Newton per meter square, right? This is a specific volume. Okay, not volume, it's a specific volume. This is a specific volume. R is called gas constant. R is called gas constant. So R is called gas constant. So if it is hydrogen, the value is going to be different. If it is nitrogen, it's going to be different. If it is carbon dioxide, it's going to be different. So depending on what type of gas you have. So for a given gas, the value is constant. But if the gas changes, the value of R is also changes. And the formula for R is Ru is called universal gas constant. This value is always constant no matter what is. And then M is called molecular weight, maybe kilogram per kilomole. So if it is nitrogen, it has certain molecular weight. If it is hydrogen, it has certain molecular weight. So you can use the table to find the molecular weight. And then Ru is a constant. See, it gives you the value. This is Ru, universal gas constant. It gives you the value at different units. So see, you can write this value in so many different unit forms. So it's important, the unit cancel out. Whenever you are doing the calculation, make sure, it's better to convert everything to the basic unit and do the calculation. And if you don't do that way, and make sure all the units cancel out and you get the desired unit. Okay, that's very important. For instance, the gas constant. So there, R is gas constant and Ru is universal gas constant, and this relation shows between gas constant and universal gas constant. For air, it is 0.2870. See, kilojoule. So you have to be careful. Kilojoule per kg per Kelvin. For helium, this is the value. So these values will be given in the table, and you should know how to make use of the table and get the value of gas constant. So this is the basic equation. Again, PV, this V, small v is specific volume, and then R is gas constant, and you can get from, I think, table A1 the value, and then T is temperature, and whenever you do the calculation, the temperature has to be always absolute temperature scale. If you are doing in SI unit, the temperature you always convert to Kelvin, and if you are using in English unit, always convert to Rankine. That is very important. So the temperature in Kelvin or Rankine. So if in SI unit, specific volume in meter cube per kg, and the pressure is in Newton per meter square, and the R is here it's given in kilojoule kg per Kelvin. So you can convert to joule so that you have everything in the basic unit and do the calculation accordingly. Okay, so this is table 1 again, which is going to be handy. And for air, like here, molar mass capital M is given here, kilogram per kilomole. This is a gas constant. So for instance, if it is given uh, helium, so the gas constant value is this. If it is given argon, this is the gas constant, this is the the mass, molecular mass. So you should know how to make use of the table, and remember this is table A1. So in the appendix you can find this in table A1, and this is going to be handy when you are using this equation PV equals to RT. So this equation can also be written in different form, like specific volume is volume per mass. So if you substitute this becomes PV. If you write capital V, this is volume, and then it becomes MRT. So in chemistry, you might have seen this equation as well. So these are equivalent. Like here. So this is our basic equation. If you convert this specific volume to uh, volume per mass, the volume would be mass multiplied by volume. So this equation is PV. In this case, capital V is volume, M is mass, so MRT. And the mass can be also written as molar mass divided by the mole number. Okay, and if you do that, this part you can substitute mr is mnr, so this should be equals to nru. So pb, again, this is volume, this is number of moles, and then ru is universal gas constant. Sometime you'll see this um, variable with this on the top, which means always per unit mole. In this course, whenever you see bar on the top, that means always per unit mole. So v is this n is number of moles, and this is volume per unit mole. So basically mole and mole cancel out, so this is volume. So you can replace that v by this, and if you do that, n and n cancel out, so this is another equation. Again, all these are coming from this equation. So this is like keeping the same equation but with the different variables. So you should know the variation coming from here, but we'll be mostly focusing on PV equals to RT, where this is a specific volume, and if you write in terms of mass, then capital V, and then it would be MRT. Okay, now this is called ideal gas equation. As the name suggests, it's not for real gas. Okay, real gases behave different than the ideal gas, and the real gas shows the behavior close to ideal gas only when at low pressure and high temperature. So that's only the case when you use this ideal gas equation, it would give you the good results. Otherwise, ideal gas equation may not give you good results. So in that case, maybe we can use ideal gas equation with the compressibility chart. That's what we'll discuss in the next class. Okay, so so this equation, ideal gas equation, gives you a good results when you have low pressure and high temperature. So again, you may have a question like, is water vapor an ideal gas? So we are saying that this equation can be used for superheated vapor. How good is your answer if you use for the water vapor? So if you see this TB diagram for water vapor at a pressure below 10 kilopascal, so here in this region, and high temperature, so this region, high temperature region, which is superheated region, you have a negligible error, so you can still use the ideal gas equation, and the error is not much. Okay, but whichever, this is called critical point. The region close to this and this superheated region at higher pressure, however, the ideal gas assumption yields unacceptable error, particularly in the vicinity of the critical point. So this is a critical point. So in this region, if you use the ideal gas equation and try to find the properties, pressure, temperature, and specific volume, then it will not give you good results. So the better would be you either use the property table, or you can use the ideal gas equation with the compressibility chart. But for a small pressure and high temperature, the ideal gas equation still gives you a good result. This is a practical case. In air conditioning application, the water vapor in the air can be treated as an ideal gas. So I think when you study about air conditioning, you have to do the calculation. In that case, you can treat vapor as ideal gas and you still get good result, because at that air conditioning system, the partial pressure of water vapor is very small, and then you can still use the ideal gas equation. When the pressure is small, then you still get the good results. Okay, but in steam power plant, where for water vapor, the pressure is really high, really high. So in that case, it lies in this region close to critical pressure and temperature. So you don't use ideal gas equation when you are using Rankine cycle where the pressure is really high. So these are kind of practical consideration which you need to take into account. Okay, now let's try to do a problem that involves um, making use of ideal gas equation. So here, what is given here? A 2 kg mass of helium. Okay, helium, again underline the keywords. So the substance is helium, mass is 2 kg, and pressure is given 300 kilopascal, and temperature is given 270 degrees centigrade in a rigid container. That means volume is constant. How large is a container in meter cube? Use the ideal gas equation. So under these conditions, you need to find the volume. Okay, mass is given, you need to find the volume. So we start with what is given. Mass is 2 kg. See, as I said before, it's important to convert all the variable to the basic unit. Like here, pressure is 300 kilopascal. Convert to Pascal. Pascal is same as Newton per meter square. Is the basic unit. Another important thing which I told you before is you should always convert the temperature to the basic unit. Since you see here, these are in SI unit, so you need to convert to Kelvin. I think you should add with 273, so it becomes 551 Kelvin. Okay. Now, so what do you have here? PV is equals to RT. So we know pressure, we know temperature. Again, this is in basic unit. This is in basic unit. R. Now we need to find the value of gas constant. You need to find the value of gas constant, and so you need to use the table A1. So in our case, gas is helium. So you need to figure out where helium is. So where is helium? Oops. So helium is here. So this is the value of R, and again you see the unit. It is in R is in kilojoule. See, remember here 2.0769 kilojoule per kg per Kelvin. So convert even this kilojoule to joule. Okay, so everything in the basic unit, so you don't have to worry about it. So if you do that, so this is the value. You convert everything to basic unit and substitute the value. So pressure in Newton per meter square. This is specific volume. This is in meter cube per kg. This is what we will get if everything is basic. This is in joule per kg per Kelvin, and temperature in Kelvin. So everything cancel out, and the final unit would be 3.76 meter cube per kg. But here, this is a specific volume. We have been asked to find the volume. The good thing is the mass is given, so we know the specific volume is capital V, which is volume per unit mass. So we know this from here. Mass is given as 2 kg, and then the only unknown is volume, from which you can calculate. So you can use this one. V is mv. and the volume is 7.52 meter cube. So um, this is the volume uh, that we need to calculate. So in the next class, we'll discuss about ideal gas equation with the compressibility factor. The reason being the ideal gas equation cannot be used for real gases, right? So it can be only used if the pressure is lower, like for water vapor. If the pressure is lower and the temperature is higher, the ideal gas equation still gives you a good result, but for higher pressure, you won't get good results, right? So that is why you need to make changes to ideal gas equation, and that's why we will discuss about the ideal gas equation with the compressibility chart, so that you can apply for some real gases. Okay, so I'll stop here. If you have any questions, please let me know. But remember, ideal gas equation can only be used for gases, okay, not for liquid, not for solid, not for liquid gas mixture, not for liquid vapor mixture, only for gases like nitrogen, oxygen, carbon dioxide, and then some superheated vapor with the low pressure for water vapor. All right, I'll stop here. Please submit your class participation work. Show the detailed work. Don't just write the answer. That's not good enough. You need to show the detailed work and submit in the Blackboard. Thank you.